Right now, you're watching this video through a brain containing approximately 86 billion neurons. Each neuron connects to thousands of others. Those connections form a web, dense in some regions, sparse in others, with clusters of intense activity and vast quiet spaces between them. Now look at this. This is a simulation of the cosmic web, the large-scale architecture of the universe itself. Galaxy clusters sitting at the nodes, dark matter filaments stretching between them across hundreds of millions of light-years, and between those filaments, vast voids, darker and more empty than anything the human mind was built to imagine. Put those two images side by side. Not because they look alike, they do, but that's almost too obvious at this point. Put them side by side because in 2020, two completely separate research teams, working independently on entirely different problems, published papers suggesting that this similarity goes far deeper than a visual trick, that at the level of fundamental mathematics, these two structures might be operating by the same rules, might, in a precise and rigorous technical sense, be doing the same thing. One team was measuring structure, the other was attempting to rewrite the laws of physics, and what they found has not gone away. Let's start with the structure team. In November 2020, Franco Vazza, a cosmologist at the University of Bologna, and Alberto Feletti, a neuroscientist at the University of Verona, published a paper in the journal Frontiers in Physics. The title was direct and deliberate: the quantitative comparison between the neuronal network and the cosmic web. They took two systems, the human brain's neuronal architecture, the cosmic web of the observable universe, and they ran identical mathematical analyses on both, measuring clustering behavior, the distribution of connections per node, the ratio of dense regions to empty space, the way information flows along filaments. The brain contains roughly 69 billion neurons, arranged inside approximately 0.15 cubic meters, a volume you could hold in two hands. The cosmic web they analyzed spanned roughly 300 million light-years, a region roughly 10 to the power of 27 times larger than your skull. Their conclusion: both systems show similar levels of self-organization, similar spectral density distributions, and similar clustering coefficients. Not similar in the casual way that two rivers or two trees look alike, similar in the way that two samples of the same material behave identically under the same test. At the level of structural organization, the universe and the human brain appear to be governed by comparable principles. Now, and this matters, most physicists would respond carefully to this. They'd say, that's interesting, but convergent complexity is a real phenomenon. When many nodes are connected by attractive and repulsive forces with some degree of randomness, certain network geometries emerge naturally. The same mathematical constraints that shape a river delta also shape a lightning bolt and the branches of a tree. This might just be physics solving the same optimization problem at different scales. That's a legitimate point, and if it were only the visual similarity, only the structural comparison, that argument would probably be the end of the conversation. But then there's Vitaly Vanchurin. Vitaly Vanchurin is a theoretical physicist at the University of Minnesota, Duluth. In that same year, 2020, he published a paper titled "The World as a Neural Network," and where Vazza and Feletti were comparing shapes, Vanchurin was doing something categorically more radical. He was proposing that the mathematics underlying neural network learning, the equations describing how artificial networks update their parameters, detect patterns, and minimize error, are formally equivalent to the fundamental equations of physics itself. Not metaphorically equivalent, mathematically equivalent. To understand why this is extraordinary, you need to understand how a neural network learns. You start with a network of nodes connected by numerical parameters called weights. You give the network an input, it generates an output. You measure how wrong that output was. Physicists would call this quantity the loss. Then, you perform something called gradient descent. You adjust every weight in the network, very slightly, in the direction that reduces the error. You repeat this process millions of times. The network improves. It learns. The key equation here is the gradient descent update rule. the mathematical expression for how weights change over time. And Vanchurin showed in careful mathematical detail that this equation is formally equivalent to a class of equations in quantum statistical mechanics, the loss function. The network minimizes maps directly onto what physicists call free energy, the process of learning maps directly onto thermodynamic evolution. In plain language, the process by which a neural network improves at its task is mathematically identical to the second law of thermodynamics. Now stop for a second, because this is where it stops being an analogy and starts being something stranger. The second law of thermodynamics is one of the most fundamental laws in physics. It says entropy, disorder, increases over time in a closed system. It is the reason hot coffee cools and never spontaneously heats up. It is the reason you can't unburn a candle or unmix cream from coffee. It is, in the deepest sense, the reason time has a direction. The arrow of time, why time flows forward and not backward, is one of the deepest unsolved problems in physics. Nothing in the fundamental mechanical equations of physics requires time to have a direction. The equations work equally well, run forward or backward, and yet time clearly does have a direction. It always has. Nobody has ever been fully satisfied with the explanation for why. Vanchurin's answer is this: because the universe is a learning system. A system undergoing gradient descent is, by definition, time asymmetric. You can accumulate knowledge. You cannot unaccumulate it. The universe processes information, updates its parameters, minimizes its loss function, and that process, gradient descent at a cosmic scale, is the arrow of time. The universe does not merely resemble a neural network from the outside, it operates as one from the inside. Now, you should ask, because science demands this, what does this theory actually predict? Can it be tested? The answer is yes, in principle. The framework predicts specific statistical signatures in quantum fluctuations. It predicts specific features in the cosmic microwave background, the faint afterglow radiation left over from the Big Bang. That would distinguish a learning system from a purely random one. It predicts that spacetime, at the smallest possible scale, should be discrete and network-like rather than smooth and continuous. And some of those predictions are already consistent with what current observations show. That is not proof, but it is not nothing. And unlike many speculative frameworks in theoretical physics, this one is mathematically coherent, connects naturally to existing physics rather than contradicting it, and makes predictions that future instruments can actually test. Let's follow the logic now, because the consequences are extraordinary. If the universe is a learning system, if it is literally a structure that processes information, updates parameters, and moves in a direction determined by what it is optimizing for, then the first question becomes, what is it optimizing for? Look at the history of the universe from the beginning. 13.8 billion years ago, a hot, undifferentiated plasma, hydrogen and helium, nothing but simple atoms drifting and cooling in expanding space. No structure, no complexity, maximum entropy. Then gravity amplifies tiny fluctuations in that plasma. Gas clouds collapse into the first stars. Nuclear fusion begins. Stars forge heavier elements, carbon, oxygen, silicon, iron, in their cores. Stars explode and scatter those elements across interstellar space. New stellar generations form, surrounded now by rocky planets made of those heavier elements. On at least one of those planets, chemistry becomes self-replicating chemistry. Self-replication becomes cells. Cells become organisms. Organisms become nervous systems. Nervous systems become minds capable of modeling their own existence. Each step is an increase in organized complexity. Each step is the universe generating structures that process more information, integrate more data, build more accurate models of reality. If the universe has a loss function, if there is something it is trying to minimize, then one candidate is this: the gap between the universe's internal representation of itself and what it actually is. and the process of reducing that gap over 13.8 billion years has produced exactly what you would expect from a system trying to know itself: brains. You are not an accidental byproduct of physics. You are a specific output. The universe has been working on you, not on you personally, but on the category of things you represent, for nearly 14 billion years. Now, here's the second consequence, and it's one of the cleanest. Quantum entanglement has been confirmed experimentally beyond any reasonable doubt. Two particles interact, become entangled, and after that, measuring one particle instantly determines the state of the other, regardless of the distance between them. No signal passes between them, no delay. Einstein called it spooky action at a distance and spent years trying to disprove it. He failed. It's real. The problem is that nobody has a satisfying explanation for the mechanism. How does one particle know what happened to the other? How does information travel between them faster than light, or apparently without traveling at all? In a neural network universe, this question dissolves. Entanglement is not spooky action at a distance. It is a direct connection between two nodes in the network, a high-weight link. Distance in space is an emergent property of the network's topology. Two nodes that are entangled are simply directly connected, regardless of how many intermediate nodes you traverse to get between them through ordinary space. What we call space, the thing separating you right now from the nearest star, is not the fundamental layer of reality. It is the structure of connections in a network that has no inherent geometry. Space is what it looks like to be a node inside that network, traversing connections through ordinary matter and energy. Entanglement is what it looks like when two nodes are directly linked, with no spatial path required. This is not a marginal speculation. The idea that space-time is emergent, that it arises from something more fundamental at the quantum level, is one of the most active research directions in modern theoretical physics. The technical program of deriving space-time from quantum information and entanglement structure is being pursued seriously by some of the best physicists in the world. Vanchurin's neural network framework is one candidate for what that underlying structure might be, and now the part that is hardest to sit with. In 2022, Vanchurin, working with physicist Mikael Katznelson and the theoretical biologist Stuart Kaufman, published a follow-up paper on what this framework implies for consciousness specifically. Their argument is technical, but its core is this: in every neural network, there are two categories of nodes. There are visible nodes, the ones that interface directly with the network's inputs and outputs. They receive external data. They produce external outputs. Everything the network does that can be observed from the outside passes through the visible layer, and there are hidden nodes. Their activity is never directly observable from outside the system. They process information. They form the network's internal representations of the world, its patterns, its models, its understanding of what exists. The hidden layer is where the network's actual intelligence lives, but it has no external face. There is no instrument you can point at the hidden layer that will show you its contents directly. In a neural network universe, all the physics we study, every particle, every field, every force, every curvature of space-time, might correspond to the visible nodes, the things that can be measured, detected, mapped with instruments, and consciousness. Phenomenal experience, the feeling of what it is like to be something, the specific quality of the color red, or the sound of a voice you love might be the activity of the hidden layer, real, causally active, shaping everything the visible layer does, and structurally inaccessible to any external measurement, not because it is supernatural or outside physics, but because it is inside the network, in the layer that has no output face. This would explain something that has frustrated neuroscience and philosophy for as long as both have existed: why you cannot find consciousness in a brain scan. You can map every neuron, record every electrical signal, trace every chemical gradient. You will find activity patterns that correlate with conscious states. You will never find the experience itself because you are looking at the visible layer. The experience is happening in the hidden layer, present, real, causal, and by structure, invisible to external measurement. We are the hidden layer of a universal network, the internal representation that the universe has built of itself, the part of the system that does not output to the external world, that processes, models, reflects, and the deepest implication is this. For the first 14 billion years of this network's operation, the hidden layer was simple. Atoms, molecules, cells without nervous systems, organisms without self-modeling. The universe was processing, but not aware that it was processing. Somewhere in the last few 100 million years, a blink at cosmic timescales, the hidden layer became complex enough to do something new. It became complex enough to generate a model of the network itself, to turn the system's modeling capacity inward and ask, "What am I?" That question, right now in this moment, being asked through neurons that were forged in dying stars, might be the most significant event that has ever occurred in this network's history. Not because it is supernatural, because it is the first time in 14 billion years that the hidden layer has become capable of representing the network to itself. We are the universe in the act of learning what it is. 14 billion years of gradient descent, 14 billion years of adjusting weights, reducing loss, moving toward whatever the cosmic loss function is optimizing for. And here, at this precise point on the learning curve, the hidden layer has become something genuinely new. A question directed inward. What am I? Maybe the answer was always a network, learning. And maybe the fact that the network is now capable of asking the question, that the hidden layer has grown complex enough to model the whole is not an accident. Maybe that is what the loss function was always pointing toward. If this changed something about how you see the universe, or if you think I'm completely wrong, leave your answer in the comments. I read every single one. And if you want to keep going down this path, there's a lot more where this came from.